Hey class, Mr. Moedin here with another video, this time dealing with linear programming and looking at optimization. The context here says an electronic store is managing desktops and laptops in their storeroom. Each desktop takes 3 hours to unpack and set up, while laptops take 2 hours apiece. The storeroom size and insurance requirements limit the store to 48 total computers at most. The store only has money for 120 hours of employee labor for the unpacking and setup. If each desktop yields a profit of $100, while each laptop yields a profit of $80, how many of each should the store sell to maximize profit? Alrighty, so quite a bit of information here. If you recall, one of our first steps in a linear programming problem is to identify the objective function. So look for the word maximize or minimize. In this case, we're maximizing profit. So we're looking for the most money. Profit is going to equal, well, something else to do with money here would be $80 for laptop and $100 profit for each desktop. So let's see, let's go ahead and define our variables. Let's call X the number of desktops and Y the number of laptops. And as such, let's see, if every desktop yields a profit of $100 and every laptop a profit of $80, that means we can express our profit in the following manner. Every desktop X brings us 100, while every laptop Y brings us 80. And this is our goal to optimize, to get the maximum value of. So now let's find our constraints, and this can be the tricky part. What are our limiting resources? What are the things we have limited amounts of? Let's look at some of the other parts of our problem here. It tells us how long each thing takes, but it doesn't tell us how much we have yet. Here's a restraint. The storeroom size and insurance requirements, they don't want you to have too much merchandise on hand in case it gets stolen, is 48 computers at most. So you can only have 48 total items on hand. So one other way of describing that, you could say the size constraint. Right? You can't have too much inventory on hand. You can't have too big of an inventory, so the size constraint. The maximum value is 48. So anything less than that or equal to that is fine. And the number of computers would simply be how many desktops X and laptops Y you have. So the total number of computers X and Y has to be less than 48. That's what this phrase here is basically saying. Right? So we're just translating it into mathematical language. Our other restraint is how much person power we have to actually work and have these things ready for sale. So we have 120 hours of employee labor. So that's our cap, right? So our labor constraints we can use less than that if possible, but at most 120 hours of wage to pay out. So we don't want to use our time the best way we can, and each item uses a different amount of time to set up. So 120 hours. How are we going to allocate that? Well, for every desktop that we have, right? Every desktop takes 3 hours. So X is the number of desktops. Every single one of those takes 3 hours to set up. So if I have only one, it takes 3. If I have 2, it takes 6, and so on. Meanwhile, laptops, a little bit less tricky, it's fewer components, only take 2 hours to set up. So laptops take, let me choose a different color. Laptops take 2 hours to set up. Choose green. 2 hours to set up. So every laptop is a Y value. Every one of those takes 2 hours, and the total must be less than or equal to 120. So there's our labor constraint. As usual, you want non-negativity. You don't want a negative number of computers. That wouldn't make any sense. So X must be more or equal to 0, and Y, the number of laptops, must also be more than or equal to 0. So if you're confused here, the rest of it is pretty straightforward in terms of what we've done in class before. The hard part, in my opinion, is figuring out from all this text, where is the actual math? And if you look at it bit by bit, you find your optimization, your objective function, rather. You have your variables laid out first, I suppose. And then you're looking for your limiting resources. I don't have room or insurance money to cover a gazillion computers, and I also have a limited number of employee time to actually pay for in order to get these computers ready for sale. So those are my two constraints. size, and labor. So let's start to visualize this scenario. I have these same restrictions here. The intercept method's a good one, so the x and y intercepts of each constraint inequality. If I cover up this guy here, 3x 120, the missing number there would be 40, and the y value would be 60. Over here is kind of easy. They're both going to be 48, right? If you just remove one, the other number must be 48. So 48 for an x-intercept and 48 for a y-intercept. If you recall, these basically tell us that we're dealing in the first quadrant. So now that we have all of our numbers, we can sort of get a sense for how big our units should be on our axes. So let's go ahead. This is a 60, by the way, not a 68. Let's go ahead and plot these. So let's see, my biggest x value, I got 40 and I got 48. Those are pretty close, but 48's a bit bigger, so let me spread that out to be around here, maybe. And then 40 would be just a hair smaller, not much. My y values are 60 and 48, so I already have 48 sort of already marked for my x-axis, so let me sort of visualize a square here. So 48 should be roughly there, and the 60 is going to be a little bit more, so maybe around there. So I kind of lost all my color coding. Let's see if I can get it back. From 60 for my y value to 40, that's going to be my labor constraint. That's something like this. And 48 apiece for my size constraint. That's going to connect those two like that. Now, what part of the figure here do we shade in? We'll keep in mind, the little trick I showed you was that when you're dealing with less than or equal to, which we are here, the side of the figure that is closer to the origin, 0, 0, is going to be your feasible region. So in this case, the parts that are below, so to speak, the red and the green would be all of this space here. So this space here is going to be our feasible region. Don't have the nice paint bucket tool here, but this will have to do. So all the possible combinations of laptops and desktops within these constraints would be in this gray space. And right away, some important points start to fall into focus. We have this one here, 0, 0, I suppose, 40, 0, as well as this point right here. And that's the one that we don't know just yet, right? We can find the other ones pretty easily. It's the intersection point that's of special interest. So let's find the intersection point by focusing on the top two restrictions. So focusing on these and rewriting them as equations in order to investigate their line properties as opposed to their shaded region properties. 3x plus 2y is equal to 120, and x plus y is equal to 48. So it'll be quite simple to eliminate one of these variables by, let me bracket these together, by, let's see, doubling the bottom. Let me make that in order to get negative 2 there, and make it negative, so negative 2. So my top restriction remains untouched, 3x plus 2y equals 120. My bottom, however, is now negative 2x minus 2y equals negative 96. So let me go ahead and compress. So these will cancel by design, giving me 0y. 3x minus 2x is just 1x, that's nice. And 120 take away 96, 4 more gives me 100, and 20 will give me 24. So x is 24. Well, let me plug that back into my original constraint. X plus y equals 24, so 24 plus y must be 48. So y must also be 24. Alright, so now we have our fourth corner point. So the fundamental theorem of linear programming tells us that one of these four, and I think we can safely assume this is not going to be it, it's really one of these three is going to be our optimal value, either max or min. In this case we want the max. So now that we have our 24, 24, let's see how that factors in. 0, 48 means we have 48 laptops only, so that's going to be 80 times 48, which is $38.40. Not bad. 40 desktops and no laptops would be 100 times 40. I'm just plugging it in right here, and that's going to give me 4,000. So that's better. Maybe this is an even better choice. Let's see. 24 desktops, that's $100 a piece profit plus 24 laptops, $80 a piece, will give me, calculated ahead of time, 4,320. So it would look like this is our best choice. Most profit by making 24 desktops, or having on hand rather, 24 desktops and 24 laptops. Alrighty, hope this helps.